Since the widespread adoption of the Internet in the mid-1990s, ever-increasing data requirements have pushed the communications industry into finding innovative ways of forcing more bits through existing communication pipelines through the use of fiber optics. Fiber has found its way into a staggering number of roles in the industrial, commercial, and mil-aero fields. It offers reliable, high-speed signal transmission over any required distance with complete immunity to the effects of radio and electromagnetic interference. Optical systems are much smaller, lighter, and more robust while offering significant cost savings in terrestrial, mobile, and mil-aero applications. The use of optical fiber provides solutions for designers, but for those new to fiber optics, the technology may seem a bit mysterious. In any given network, a complete lack of signal may be a relatively simple problem to diagnose. However, optical networks often suffer the effects of degradation rather than a complete failure, leaving even experienced people scratching their heads. There are many possible sources of signal degradation ranging from issues with system electronics to the fiber itself. Many issues depend on whether the signal is analog or digital. Analog signals, such as those in sensor systems, can be more sensitive to signal degradation than the more forgiving digital systems. Some of the most common problems, as well as some of the most vexing, can occur in optical connectors. These can be mechanical issues with fiber, ferrules, or termini, or procedural issues such as contamination and poor handling methods. How, then, does one proceed to isolate and resolve some of the more mysterious system problems that may appear? Narrowing problems down so they can be efficiently corrected requires a basic understanding of optical fiber, connectors, and optical signal transmission. An optical fiber is made up of three parts. The first and outermost component is the coating. Made from plastic materials, the coating provides protection against bending, damage to the glass surface, environmental effects, and mechanical stress. Under the fiber coating is a layer of cladding, usually made of pure silica glass. The function of the cladding is to prevent light from leaking from the fiber. While most fibers used in communications have a cladding diameter of 125 microns, other cladding sizes may be employed for different applications. Beneath the cladding, the core is the part that carries the optical signal. Like the cladding, the core is also made of silica, but is doped with certain elements to change its refractive index with respect to the cladding. This refractive index difference allows for light to be totally internally reflected within the fiber core. Light launched into an optical fiber within a small angle of its axis will be transmitted to the opposite end. The structure and chemical makeup of the core is critical to fiber operation. Optical fibers are divided into two broad categories, multimode and single mode. The major physical difference between them is the diameter of the core. Single-mode fiber has a small core diameter compared to the overall fiber diameter. The small core size forces light to travel in a single pathway or mode down the axis of the fiber at a single wavelength. Multimode fiber has a much larger core diameter, allowing the optical signal to take a number of pathways from one end of the fiber to the other. The fundamental mode travels down the fiber axis, while higher-order modes will take a number of longer alternative pathways. Multimode fiber is specified in micrometers, with core diameter first, followed by the cladding diameter. Common examples are the 50, 125, and 62.5, 125 fibers. Single-mode fiber does not need to address the propagation times of different modes. Unlike multimode fibers where optical power distribution is entirely within the core, light transmission within single-mode fibers assumes a Gaussian distribution. Depending on the wavelength of operation, approximately 80% of the light travels within the core, while 20% travels in the surrounding cladding. The total diameter of the resulting light spot is called the mode field diameter. At 1310 nanometers, mode field diameter can range from 8.6 to 9.5 microns with a plus or minus 0.7 micron tolerance. The larger the mode field diameter, the easier it becomes to splice and terminate, but the more sensitive the fiber is to bending losses.